Okay, thank you, Takayuki. Yeah, the topic is data-driven site characterization for the benchmark examples using sparse Bayesian learning. I would like to thank Ikumasa and Takayuki for organizing this forum on behalf of TC304. Also, I would like to thank KK and Takayuki for preparing the benchmark examples. Yeah, the method that we use is called sparse Bayesian learning. It was developed in computer science in 2001 by Michael Tipping, but in fact the main idea it can be dated back to Professor McKay in 1992. The basic idea is to ask the question, what is the most plausible small set of basis functions that can fit the data? Say, for instance, this is a regression problem. If you use a lot of basis function, then you can easily overfit the data. But if you only allow a small set of basis function, then you may get this more reasonable trend. For classification problem, you have the similar situation. Basically, what Professor McKay, what he did is to construct a probabilistic model that uses a strongly favorable prior towards zero variance of sk squared. This sk is the variance of the weight for the case basis function, and your trend function is equals to the summation of the basis function, and the wk is the weight. So wk is modeled as a zero mean random variable, and the variance is sk squared. For the model constructed by McKay, this sk is a hyperparameter with a prior distribution strongly favorable to zero. So that means unless you have sufficient evidence, otherwise the posterior distribution for sk will have a peak at zero. A peak at zero, that means wk is close to zero. So the case basis function is inactive. So it is kind of a similar idea with the G lasso that is mentioned by Takayuki. This is a sparsity idea. The main difference is that here the sparsity is imposed on the weights of a basis function, but in G lasso the sparsity is placed on the difference between x, the difference between x in the Takayuki's G lasso method. So we adopt the similar sparse Bayesian learning idea in 2017, and we develop you can say it is a geotechnical SBL. In this version, we incorporate correlated noise. This is quite important. In the original SBL method developed by Tipping, the noise term is assumed to be white noise. but we all know that for geotechnical engineering, the spatial variability is correlated. And also in this paper, we only consider one-dimensional problem with trend represented by Legendre polynomials as basis functions. And this, we use a two-step algorithm in this paper. Step one, we do basis function selection. However, we found that the solution provided by the original SPL is not sparse enough. So we develop a extra thresholding criteria to remove even more basis function to make the it even more sparse. And step two, we draw conditional samples of the trend functions, and the COV of the random field, and the scale fluctuation of the random field. So it is a two-step algorithm. And in 2020, we extend the 1D algorithm to three-dimensional, and we take extra efforts to make all the formulation into chronicle product representation for lattice data. By lattice data, I mean if all the soundings measure the same depth, then it is called the lattice data. And if some of the sounding they do not measure the same depth, then this is non-lattice data. So it assumes lattice data. Also in this paper, we develop a step three. The purpose of step three is to do a three-dimensional conditional random field simulation. And also in this paper, we adopt the more versatile Whittle midterm model as our autocorrelation model. And then recently, we extend to non-lattice 3D data so that now the 3D SPL can analyze non-lattice data. And the method I want to demonstrate today is this method, because the data we're given are lattice data. Let me use this page to briefly explain how 3D SPL is working. I use G1, T1 as example. So this is ground one. T1, it has 3 measured soundings, and there are 12 validation soundings. Step one, basis function selection. Well, this is just one picture, shows the solution of step one. This is the optimum solution for SK. So you see this axis is the vertical basis index. We take 20 Legendre polynomials as the basis function for the depth direction. For the horizontal direction, we take 4 basis function. And as you can see, there are only a very limited number of solutions here. For the basis function that without a solution, that means the optimal SK solutions is 0. So you see, after the step one, there are only limited number of basis function remaining. However, we found that these basis functions are still are not sparse enough. So our extra thresholding algorithm, it finally picks up only 4 basis function here. So that's step one. Step two, purpose is to draw conditional samples for the trend. This is the 3 samples of the trend function. This is the 3 observed sounding 1, 2, 3, and those 3 red lines shows 3 samples of the trend functions. We can also draw conditional samples for the Whittle midterm parameter, scale fluctuation, smoothness. This is 1,000 samples of them. Horizontal scale fluctuation, smoothness, and standard deviation. So this is step 2. Step 3, we simulate 3-dimensional conditional random fields for the 12 validation locations here. You see the green lines represent 1 realization of the conditional random field. Solid line means the sample median for the 1,000 random field samples. Dashed line is the 95% confidence interval. Okay, now let me show you the result for G1, T1. And but in this page, I want to address the question: does sparsity really matter? Let's consider SBL versus non-sparse method. By non-sparse method, I mean we do not throw away any basis function. We keep all the Legendre basis function. There are many Legendre basis function. If we keep all the basis function, the green line shows the 1 sample of the trend function. You see, this is kind of overfitting. Note that I am talking about trend function here. I am not talking about simulation. This is the trend. The green line is really kind of overfitting. The red line is the SBL result. It kind of not overfitting. This is the step 3 result for SBL. You see the red line here represents the actual measured data at the 12 validation soundings. So you can treat the red line as the actual answer. And you see 95% confidence interval. They are quite effective. This is for sparse Bayesian learning. If we take the non-sparse solution, then it is very ugly. You see the median is the black line. It oscillates a lot. You cannot even see the dashed line. The dashed line is so wide that you can see it in this upper limit and lower limit. You can see kind of 95% confidence interval for this sounding. And this is the rooming square error for the QT for this G1, T1 case. 3D SBL is red dots. Green dots is the non-sparse solution. You can see 3D SBL is much better than the non-sparse solution. A byproduct of our algorithm is the evidence of the training data. This capital D means the training data for the 3 soundings. This is the evidence, log evidence for the sparse, for SBL. This is for the non-sparse method. You see the evidence for the sparse method is much larger than non-sparse method. The type of basis function has also some effect. Previously, I talked about a Legendre basis function. This figure shows you the 1-dimensional Legendre basis function. There are lots of them here. Here, I only show you the first 3. The 0 order is a constant. First order, linear. Second order, quadratic. I also consider another type of basis function. I call it step basis function. Basically, this is these are the Heaviside functions. Phi0 is the Heaviside function with jump point at 0 depth. Phi50 is also a Heaviside function. Jump point is at 4. Here you see the amplitude of the Heaviside function is different because in this plot I normalize the norm of the basis function to a constant. Well, the reason I investigate this basis function is because for the benchmark example that Takayuki gave me, the actual underlying trend are often step functions. So I thought step basis function may provide some advantages. For Legendre function, it is very difficult to model the step using finite basis function. Okay, this is the result for G1, T1. This is the simplest ground scenario. Red line is the one sample of the trend function for Legendre. Green line is one sample of the trend function for the step basis function. You see, for the step basis function, it is kind of interesting. It kind of match the step-like trend in the data. By the way, for the step basis function I use here, I only consider the step in the depth direction. I do not consider the step in the horizontal direction. I mean, the horizontal basis function is a constant function without any step. But for the Legendre polynomial, in the horizontal direction, I allow linear variation. I adopt 4 basis function in the horizontal direction for the polynomial, for the Legendre polynomial. Okay, this is the conditional random field for the Legendre basis function. You see, although Legendre basis function is not ideal for the step-like trend, but the conditional random field still quite makes sense. And this is the conditional random field results for the step basis function. So you can see, I think it is even better. For this particular example, if you look at the evidence, you see the step basis function has higher evidence. Also, the step function has smaller root mean square error. That's for G1. How about G3? Now let's consider G3, T2. T2 now has more sounding. You see, for this one, I want to show you the step function, step basis function. It does not always outperform Legendre function. Even though the actual underlying trend is actually quite similar to a step function, but for this particular example, a Legendre polynomial actually outperform step function. You see, say for instance, for this location, the step, the green line, it doesn't catch this step. Okay, this is the result for Legendre polynomial, and this is the result for step function. And you see, Legendre polynomial for it has higher evidence, and also its root mean square is smaller. Yeah. Now, this is the G2, T1, T2, T3. I show this page because Takayuki sent us this, send the G-lasso result to us, so that we can do a direct comparison. This is the result for 3D SPL with Legendre basis function. This is a step basis function. And I guess it's quite promising that G-lasso sometimes it does very well for something, say for this guy and for that guy. For those two soundings, 3D SPL cannot beat G-lasso. But in general, 3D SPL, it has quite uniform performance. Even if we have layout 1 means T1, T1 means that we only have 3 soundings observed. Even if we have only 3 soundings, the performance is not that bad. This shows the comparison for QT. This page shows the comparison for IC and the identification rate. This figure was provided by Takayuki to me. This is the result for Legendre step function. You see for this G2 example, Legendre is not good. The identification ratio is significantly smaller than G-lasso. But for T1, it is not terrible, not terrible. But if I change to a step basis function, then this performance is comparable. For T1, the performance is quite well, is quite good. And here I shows the evidence for Legendre basis and the step basis to you. You see usually the step function basis, it has higher evidence. So that means this is preferable. Okay. I guess I may not have much time to show a lot of those results, but we also this is, well, I focus on T1 here. G1, G2, G3, G4, it represent the difficulty of the ground model. G1 is the simplest. G4 is the most complicated. And indeed, for the simplest one, usually we get the least root mean square error. But for the other 3, G2, G3, G4, it really depends. Sometimes G4 is not the most challenging example to SPL. Say for instance, G4, you see SPL perform quite well for G4. Okay. So computational cost. Here I shows the computational cost for G-lasso. For SPL, the computational cost is not very high. This is step 1, and this is step 2 plus step 3. 87 seconds is the time required for Legendre basis. Legendre basis. This is the time required for Legendre basis. So you can see it can finish in minutes. Okay, conclusion. I guess I do not have time for conclusion. Maybe I stop here. Okay, thank you.